Today we're going to begin our talk about finding volume of what we call solids of revolution. So a solid of revolution is just a geometric solid that is obtained by taking a region in the coordinate plane and revolving it around a line. So even though we know the formula for the volume of a sphere, we're going to see if we can find a way to use this semicircle that has a radius of 4 by revolving it around an axis to find the volume of a sphere that has a radius of 4. So if I were to take this semicircle and revolve it fully around the x-axis, as if it came out of the screen towards you, and then back into the back part of the screen, and back up to where it started, a full 360-degree revolution about the x-axis, we'd end up with a sphere that has a radius of 4. And the nice thing about a sphere is that no matter which direction I slice it, the cross sections are always going to be circles. It doesn't matter if I do it diagonally, vertically, horizontally. The cross sections will always be circles. So we're going to just take this and slice it perfectly vertically into an infinite number of little slices here that have infinitely thin width to them of dx. And because those cross sections end up being circles, circular cross sections, we know that the area of the face of one of these cross sections is pi r squared. And since the width is dx, all we would need to do is integrate pi r squared dx from the left bound of our region to the right bound of our region, from -4 to 4. But we can't do this because we have two different variables, so we have to find a way to turn r into terms of x. Well, the radius of this cross section, if this is our little cross-sectional piece right here, this little sliver of a circle, that has a radius that extends from the x-axis up to the function. It's just y. And we should know the equation for a semicircle. The equation for any semicircle is the square root of the radius squared, so in this case 4 squared, minus x squared. And that's an important thing to know. This is a semicircle that, if it was the full circle, would be centered at the origin, and it has a radius of r, and it's the semicircle that sits atop the x-axis. If we had a negative in front of it, it would be the one that's below the x-axis. So now we know the value of r. R is our y, or root 16 minus x squared. So we should be able to plug that in here into our integral. Pi times the integral of 16 minus x squared dx. And because r was the square root of it, and we needed r squared. And then we'll just integrate, giving us 16x minus x cubed over 3 from -4 to 4. And we'll go in and we will evaluate this. End up with 64 minus 64 thirds minus -64 plus 64 thirds. And 64 minus 64 thirds is 128 thirds. So this is 128 thirds minus -128 thirds, which would be 256 thirds. When we multiply that by pi, we get 256 pi over 3 units cubed. And we can see that if we've gone in and used the formula for the volume of a sphere, where volume is 4/3 pi r cubed, we would have gotten this exact same value. So let's see if we can, in generic terms, just with a semicircle of radius r, see if we can prove that the volume of any sphere with a radius r is always going to be 4/3 pi r cubed. So we're effectively doing the exact same thing we were just doing a minute ago, except now the semicircle that we're looking at, which we're going to revolve around the x-axis to turn it into a sphere, just has a radius of r. It goes from -r to r. And the cross sections will still be circles. So we're going to want to integrate from negative r to r, pi times our radius, which in this case, that radius is that same thing, y, which, well, let's call this, since we've already called these little r, let's call this big R. That radius is y, which is the square root of r squared minus x squared. So if we need pi times that radius squared, that'll just be r squared minus x squared dx inside of our integral. And here, it looks like we're looking at two different variables, but in reality, the little r is just a constant. It's just the radius of this sphere. So r squared is just a constant. And so when I'm integrating r squared, it's just the constant times x, since the variable we're looking at is dx. The integral of r squared dx is just r squared x. And the integral of x squared is x cubed over 3. And if we evaluate that from negative r to r squared x evaluated at r is r cubed. We have r cubed minus r cubed over 3. And then minus, when I plug negative r in, that's a negative r cubed. And a positive r cubed over 3. And both of these become 2/3 r cubed. You have 2/3 r cubed minus negative 2/3 r cubed, which is 4/3 r cubed. And multiplying it by the pi gives us the volume formula for a sphere that we should be familiar with already. So, nice little trick to prove the volume of the sphere is 4/3 pi. So we're going to apply this idea to basically any function that we're interested in looking at. And mostly today we're just going to do some simple ones, and then next time we'll move into some more difficult ones. Today we're just going to be revolving around the x-axis, and then the last couple problems will be revolving things around the y-axis and doing stuff in terms of y. So for this one, we've got the region in the first quadrant enclosed by the x-axis, the y-axis, and root cosine x, so that region that we've shaded right there. And we're going to revolve that region about the x-axis. So as I do that, I'm just going to get something that looks a bit like that, maybe like the bottom part of 8 or something. And because the cross sections, when cut perfectly vertically, which have a thickness of dx, are circles, we're just going to use the same idea that it's pi times an integral of the radius squared dx. And we're going to integrate from 0, the beginning of this region, to wherever root cosine x equals 0 again. The cosine of pi over 2 is 0. So this would be when x is pi over 2. But of course, we can't integrate r squared dx. We need to turn that into terms of x. So just like the other one, our r value here is the radius. It's from the x-axis to the function. That's just the y value for root cosine x. So when I plug that in, I really just end up with pi times the integral of cosine x. So when I square the square root of cosine, I get cosine from 0 to pi over 2. And the integral of cosine is sine. So we've got sine x from 0 to pi over 2, which gives us pi times 1 minus 0, or just pi units cubed. For this one, we're taking a look at the function 2 plus x cosine x. And we're going to take the region between -2 and 2 and the x-axis for this and revolve it around the x-axis to generate a solid. Now, this picture is not going to be perfect here, but we're going to end up with something that looks kind of like this, right? It's got an end right here at negative or at +2. And then we revolved it around. It kind of looks like, if you look at it sideways, it kind of looks like a flower vase. And so The same concept's going to apply. If we slice this thing perfectly vertically, the radius of the circular cross section is just the y value, or 2 plus x cosine x. So we should be able to go in and write pi times the integral from -2 to 2 of r squared, or 2 plus x cosine x squared dx. And even if we try to distribute this out, this is going to be a fairly difficult integral to find. It's Calc 2 integral requires integration by parts. So we could go ahead and use our graphing calculator to see if we can figure out the actual value of this integral. So we'll hit math, option 9, FNINT, and we're integrating from -2 to 2 of 2 plus x cosine x squared dx. And that gives us like 16.688618868. And if we multiply that by pi, because we had a pi out in front of it, looks like we get 52.429. For this one, we're going to look at something just slightly different. So now we've got the region between y equals x, this upper diagonal line, y equals x over 2, the bottom diagonal line, and the vertical line x equals 5. And we're going to take this and revolve it around the x-axis. So if we do that, I think we should note that the difference here is we don't actually end up with a circular cross-section, right? Because as we revolve this around, this gap that we've got, that I'm going to kind of shade in here in red, this gap here is causing a big cone-shaped hole in the middle of our bigger cone. So what we've got here is actually a cross-section that looks like a circle with another circle cut out of the middle. So all the other ones were just discs, and we call those the disc method when we use pi over squared. These look like washers, so we're going to call this the washer method. In order to find the area of one of these cross sections, we just need to find the area of the bigger circle by using pi times that outer radius squared. And then we need to subtract from that the area of the inner circle, pi times the little radius squared. Or effectively, we're just going to do pi times the integral of the outer radius squared minus the inner radius squared dx, because the thickness of this is dx. And in this case, from 0 to 5. And so we just need to figure out the values of big R and little r. Well, big R extends from the function on top, the upper bound of our region, all the way down to the x-axis. Well, big R then is just x, because that's that function, y equals x. We've got pi times the integral from 0 to 5 of x squared minus that little radius is just from the lower bound of the function of the region to the x-axis, so that's x over 2. So minus x over 2 squared dx, which will give us pi times an integral from 0 to 5 of, well, x squared minus x over 2 squared. X over 2 squared is 1/4 of x squared. So 1x squared minus 1/4 x squared is 3/4 x squared. And we can then integrate that, which gives us pi times x to the third over 4 from 0 to 5. And if we plug in 5, that gives us 125 pi over 4, and subtracting 0 effectively does nothing. And we're just left with this as our result, 125 pi over 4 units cubed. And so we'll note that the only difference here is that our region wasn't fully pushed up against the axis we were revolving around. So when that happens, right, when there's this gap that we've got in here, right, this gap in here between our region and the axis of revolution, that gives us a washer cross section. I can do this outer radius and inner radius and subtract them. So this is just the formula that we came up with, pi times the integral from a to b of big R squared minus little r squared dx when we're going around the x-axis. But a very common mistake that we run into, I see students make all the time, is that they'll do big R minus little r and then square it, rather than squaring each radius first. So just be aware that this is not the right thing to do. Don't do this. It's a very common mistake that people make, but it is not correct. So make sure you don't do it. Let's do another one of these where we're looking at the region in the first quadrant enclosed by the y-axis. Y equals cosine x and y equals sine x. So the y-axis, cosine x and sine x, would be this region right here. And we're going to revolve that around the x-axis. So part of it's going to look like that, and the other part of it's kind of going to look like this. And we end up with, again, we end up with these washer cross sections because our region, right, this region, wasn't fully pushed up against the axis we were revolving around. It creates this big gap in here in the middle. We have washer cross sections. And so we have to do a couple things. One is we know it's going to be pi times an integral from 0 to this intersection point. And make sure you always indicate how you find that intersection point, even if there's no algebra to do, right? Sine x equals cosine x, and then say that's at x equals pi over 4, because we know that both the sine and the cosine of pi over 4 is root 2 over 2. So we're going to integrate from 0 to pi over 4 of our outer radius squared. Our outer radius is just extending from this upper function down to the x-axis. That upper function is cosine x. So this will be cosine squared x. And then we'll subtract our inner radius, which just comes from the lower function. That one's just sine x. So cosine squared x minus sine squared x dx. And we should know that cosine squared minus sine squared is equal to cosine 2x. If you're not familiar with your double angle identities, your trig identities, you really do need to know those. Makes life a lot easier, because if you don't know that, the only other option really here is to use the power reducing identities. And if you don't know the double angles, you probably don't know the power reducing ones either. And so really, we just want to turn that into cosine 2x, integrate cosine 2x into 1/2 sine 2x, and evaluate from 0 to pi over 4, which gives us pi times 1/2 the sine of pi over 2. Since the sine of pi over 2 is 1, that's just 1/2. And then minus 1/2 sine of 0, which is just 0. And we end up with pi over 2. Just a couple more. This next one, we're going to take a region and we're actually going to revolve this around the y-axis. So it's going to be a little bit different than the ones we've done here previously. So we've got the region between y equals x squared and the y-axis. So we're talking about something inside of here, from x equals 0 to x equals 2. So if I go up here to the point 2, 4, we're going to talk about this region right here. And we're going to revolve it around the y-axis. So if we do that, if we revolve this around the y-axis, we can see that in order to get circular cross-section, we're going to have to slice this thing perfectly horizontally, right? We're going to go perfectly horizontally through here, and it's going to have a thickness of dy instead of dx. So now as I do this, I'm still going to have pi, and I'm still going to have an integral of a radius squared, but now it's dy. And so I'm going to have to do two things. One is I'm going to have to make sure that my limits of integration are y values. So I'm going to go from the lowest y value, which is 0, to the highest y value, which was 4. And then I also have to figure out what the radius of these cross sections are. Well, that's from here to here. That's our radius, which is just an x value. It's just x, right? It's just a distance from the y-axis over to the function over here, right? Which is always just a distance of x. But we need it to be in terms of y. So we need to go back over here and say, oh, well, if y is equal to x squared, then x is just equal to root y. So our radius is just root y. We can replace this now with pi times the integral from 0 to 4 of root y squared dy. Well, obviously, root y squared is just y. So the integral of y is y squared over 2. And we'll evaluate from 0 to 4. We've got pi times 8 minus 0, or just 8 pi units cubed. So this is the last one that we're going to look at today. We're going to take the same function, y equals x squared, and we're still going to look at it from x equals 0 to x equals 2 over here, so this region, between that and the x-axis. So we're talking now about the other side of this parameter. And we're going to take that and revolve it around the y-axis. So we're effectively going to get another thing over here that looks kind of like this. And as I revolve this around, we can see that in these places up here, I've got washer cross sections, right? Because this region is not fully pushed up against the axis that we're revolving it around. So these have a thickness of dy. So we're going to do pi times an integral from the bottom of the region, 0, to the top of the region, 4. Again, that's the 0.24 up here. Of the outer radius squared minus the inner radius squared dy. And our outer radius is going to extend from the x-axis to the rightmost bound of this region. Well, the rightmost bound of this region is always defined by the line x equals 2. Everywhere from y equals 0 all the way up to y equals 4. X equals 2 is the right bound of that region. And so that distance doesn't ever change. That distance is always 2. So our outer radius is 2. So we'll do 2 squared. And then our inner radius just extends from the y-axis to our function, which is just some distance x, but it's x that is related to the equation y equals x squared. So x is equal to, again, just like the last one, root y. So this is 2 squared minus root y squared dy. Or it's pi times the integral from 0 to 4 of 4 minus y dy, which we should be able to easily integrate to get pi times 4y minus y squared over 2. We'll evaluate that from 0 to 4. Plugging in the 4 gives us 16 minus 16 over 2, so 16 minus 8. And then the 0 just gives us a whole bunch of 0 over there. And interestingly enough, by coincidence, this ends up also being 8 pi units cubed. And so that's how we are able to find the volume of solids of revolution. We're going about the x-axis or about the y-axis. And so next time we're going to look at some more complicated ones where we are either revolving around lines other than the x or the y-axis, always horizontal or vertical. We're not going to revolve around things like y equals x or y equals 1/3 x plus 5. It'll always be a horizontal or vertical line. So next time we'll revolve around other lines, not just the axes. And we'll also take a look at some where we have to break up our integral into multiple different integrals in order to be able to solve it. And that's it for this time. We've just got a couple more lectures for the year to go.